Good day. In today's video, we are going to derive what we call the wave equation. So first, let's see here a part of the string that used to oscillate up and down, and that will definitely generate a wave. Okay, and as you can see that this part of the string, okay, we're going to designate this position as x, and at some distance that will be x plus delta x. Okay, and we all know that that at both ends of the string we have a tension T. Okay, so those two tensions are definitely equal to one another. Okay, this is the increasing value of y, and that is the increasing value of x. Suppose that the direction of wave is going to the value of, is going to the direction of positive x. Okay, we have here mu. Mu stands for mass per unit length. Okay, I'm going to designate delta m as a tiny piece of mass over delta x, which is a tiny piece of length. Okay, and and delta m over delta x will give us mu, which is the mass per unit length. If this is x plus delta x and this is x, definitely this length is delta x. Okay, I also have here theta 1 and theta 2. As you can see, those two angles are not equal. If those two angles are equal, then definitely that amount of tension is the same, and so what will happen here is that the string will not oscillate and the string will just be a straight line. Okay, so definitely there must be something on the differences on those two angles. Okay, so we have here some values that we're going to use later in our derivation. Okay, so what would be the equation that will fit this scenario? Okay, we're going to use Newton's second law, wherein the the sum of the forces. Okay, since this is moving, this string is accelerating. It is only accelerating along the y. So the sum of the forces of the tensions is equals to ma. Okay, so let me explain this one furthermore. So what would be the sum of the forces here? So we have here t sine theta 1 minus t sine theta 2. Okay, why do we choose sine theta, not the other trigonometric functions? Because we only care about the vertical composition of the tension. Okay, why? Because as we said before, the string is only moving along the vertical. The string doesn't move along the horizontal. You will see that if I'm going to place a point here, okay, as the string goes up and down, it doesn't change its horizontal position. Okay, but the x position is constantly changing. Definitely it is accelerating only along the y, so we only care about the sine of the theta, the vertical component, these vertical components. Okay, so if we're going to get their difference, that would be equals to delta may. So this is the mass present in this tiny piece of string times a sub y, which is the acceleration along the y axis. Okay, now we have here the Taylor expansion for sine theta. Okay, sine theta is approximately equals to theta minus theta cube over 3 factorial and so on. That is the Taylor expansion. That we use this one for approximation. If you're going to plot this one in the calculator, that will give you almost the same values for sine theta, provided that you are only within a very close range near the x-axis. Okay, for very small angles we can disregard this one. So we can see now that sine theta is the same as theta. So I can write this one as t theta 1 minus t theta 2 is equals to delta ma y. Okay, so next you will see here that theta for very small angles, okay, is approximately the same as tan theta. Okay, for very small angles, we can remove those additions. Definitely, I can write this one as t. I can factor out this t. That becomes theta 1 minus theta 2, right? Theta 1 minus theta 2 is equal to delta ma sub y. Okay? Now, what is this difference? Okay? Theta 1, if we're going to use tan theta, that would be y over x at that position x plus delta x, right? That would be y over x at position x plus delta x if we're going to use tan theta. And theta 2 is y over x at position x. You see? So let me write it here. That would be t. So that would be dy dx at position x plus delta x minus dy dx at position x. Okay, do you follow? Now, why do I use partial derivatives here? Okay, so here's the catch. Why there's a partial derivative, not the typical dy over dx? Why? Why is that? It is because at this very moment in time, let's say I'm going to freeze the time, so the string will be bent in this way, okay? The time is not moving, it is being stopped. Then you will see that y and x is only changing with respect to position. The tangent of theta is only changing with respect to position. If I'm going to move further more in this direction, then that value of y of dy over dx will also change. Okay? So that is the explanation why do we use partial derivative here. Okay? Because on the other hand, this will be equals to delta m. Now, what is the acceleration along the y? We know that the acceleration is the second derivative, time derivative of y, because that is pertaining to y. So I can write this one as d2y over dt square. Okay? You get it? That will be d2y over dt squared. That is the second partial derivative of y with respect to time. Okay, because on the other side, this would be the partial derivative with respect to position x. Okay? Mu is delta m over delta x. Therefore, I can rewrite delta m as mu times delta x. So let me write it here. I can write this one as mu times delta x, right? This is the same as delta m. Mu times delta x is the same as delta m. Okay, now, how about this one? How are we going to deal with this difference? Okay, so let us proceed to this one. You will see that this is the fundamental theorem of calculus. This will give you the derivative of a function, wherein the derivative of x, f prime of x, is equal to the limit as x approaches to 0 of f of x plus delta x minus f of x over delta x. Okay? Suppose that this term is this term. You see? Because of the x plus delta x. And this term is this term. Because we are only talking here about the position x. Okay? So if I'm going to place delta x on this side, taking out the limit definitely as delta x approaches to 0, then this function, this difference is equals to the derivative of this side, which is before that is equal, times delta x. Okay, so I can now write this one as t. So what would be the derivative of this one? That would be the second derivative, d2y dx squared, that is the second derivative, times delta x. Okay, because that is the derivative. This is the second derivative. Why? Because we already have here derivative, so definitely the answer here will be second derivative. That is now equals to mu d2y over dt squared delta x. Now we can cancel this delta x, and so you will see here that d2y over dt squared is equals to t over mu times d2y dx squared. This is what we call the wave equation. This is for physical waves, like string. Okay, you will see that this equation, this is a differential equation. If you're going to get the second derivative in time, you're going to get the second derivative with respect to the position of y. Okay, and then we have here the tension over mu, which is the mass per unit length.